Looks like we're about there. Welcome back, everyone. And it's official. Looks like we can start. So today's class, we're going to be moving through section 6.3 into section 7.1. But the bigger announcement is our second exam is going to be Monday of next class. That means we won't actually hold class this day. This is all about just getting through that exam day. And the reason we don't hold a class on an exam day is because it just feels like you'd be too on the hook for too much during the week. Doing a 50-minute exam and then two 50-minute classes is just more than we've signed up for on any given week for a 2-credit class. And so if you did come into the Zoom and it's empty, that would be why. Usually there's a couple people that come into the Zoom on an exam day. I would imagine it's just you're a creature of habits or just used to doing that. And again, that's why we won't be having class on that particular day. So this exam is the first one that's going to be Open Calculator. A basic scientific calculator can be used. And if you're not sure if yours is allowed, email me right away and I'll be happy to let you know. For general guidance on the math department's policy on the calculator and the note card, you can see this PDF right here. And really, we haven't used the calculator in a very major way. This is the first time the calculator is going to be allowed on exams. It'll be the same for exam 3 and the final exam. The question it helps most with is the 5.4 question. We're going for exact answers on that one, but in a couple spots, it just is nice to have a little bit more computational power for getting that right triangle in line. Well, for the breakdown of the exam, you can see these random arrows that are pointing at the 3 sections. I'm only going to ask one question from section 5.4. In section 6.1, we did transformations of sine and cosine. And I could ask for both, but this is a 50-minute exam, so to keep it about the right length, I'm going for 4 questions. So I'm randomly selecting one of the two, either a sine or cosine graph. And amongst these 4 graphs here, I'm going to randomly select one between cosecant and secant, and one other one between tangent and cotangent. So that's what's going to make up our second exam. Well, any questions at the moment, folks? Okay, ways you can prepare for the exam are definitely the most important way by far, and this is really by a huge amount, is just being caught up on the homework. Work those problems as if they're real exam questions, as if they're high stakes, try to get all the details in. Work these problems knowing that we won't have a graphing calculator. We have to know how to do these with minimal assistance, really knowing the properties of those trigonometric functions. And the moment you get these sections completed, I'll send in the feedback to let you know how you did as soon as possible, trying to get it all done before Monday. So even if you send me homework late on Sunday, I'm going to make every effort possible to get it graded first thing Monday morning to get your feedback sent to you. If it comes in, say, like 10 a.m., between noon and 10 a.m. on Monday morning or later, it's going to be kind of sketchy if I can get your feedback, but I'll still try to make an effort. So getting the homework done, even if these 2 sections have gone past due, section 6.2 is due today, I still accept these for full credit because it really is that important for learning the content and preparing for the exam. But additional things you can look into are the sample exam version 1, version 2. Version 1, because we made a lot of homebrewed problems, is more of the same kind of problems that you can take a look into. This is problems out of the book. This would be a good roundup of the problems you can see as typical exam problems. I think this was an actual homework problem, but it was a good one, so I put it on that list. Then these are the ones that I invented again, same instructions as we've seen before, so same expectations for credit. And I have the answers at the very bottom of this document for the custom-made exercises. The ones out of the book you can see in the back of the book for the odd problem solutions. Version 2 are the actual lecture notes with all formulas taken out. It's just the problems all alone. So the solutions to these you can find on the Canvas website just by, say, going back to section 5.4 and pulling up the PDF right here, which is now has its solutions. So really, this is nothing special. It's the same problems all over again, but it's something you can print out now, work through as an actual worksheet, and get through this kind of content. The problems are just as good as before. I don't think seeing this problem again would have perfect memory on how it goes, so it's still equally valuable for extra practice. Really, the way we're setting up exam 2 is pretty much identical to how we did exam 1. We'll do the same for the third exam, same kind of materials, and the same for the final exam, just longer documents here. Well, that's the roundup of announcements getting into our upcoming exam. Also, earlier today, I sent a reminder on how to schedule your exam. So if you didn't see that come through your ISU email or through the Canvas inbox here, let me know right away, and I'll let you know the instructions for getting it scheduled. But any questions whatsoever, folks, before we start back in section 6.3? Okay, well, in 6.3, we're like 2/3 of the way through this section there. So we'll also be turning to section 7.1 at the end of the class today. And here's where we left off. There's lots of information we're looking into. The key thing is we're dealing with the cosine function, working with the domain and the range of the restricted cosine function and the function inverse on the right. So let's go over a couple of how these went. So if we took a look at, say, this one, cosine inverse of 1/2, we said the answer was pi/3, but the thought is what we do is we begin by getting the drawing tools going. So let me fix that. We take the 1/2 because it's a cosine function. We place, I think we are looking up here. I think I messed up my document. Hang on. There's always a way to fix that with enough Control-Z applications. Okay, I think it's all back. So cosine inverse of positive 1/2, there's where it was plotted finally. We took the 1/2 and just put it right here on the unit circle. It's on the x-axis because it was a cosine function. Then we notice there is one angle, one unique angle between the range from 0 to pi, such that cosine at that angle does give a half. So once we found that angle, we just brought it down here, and that ended the process. So step 1 was to go to the x-axis. Step 2 was to find the angle. And it's a complete reversal of how we did it in section 5.2. Cosine pi/3 would have started on the angle, gone down to the x-axis, and grabbed the value 1/2 for the output. So that's the rough review of how every one of these trigonometric functions go. The other big punchline is because we're dealing with a bona fide function inverse, the other concept is we're just swapping the input to this function, making the output to the inverse, and likewise the input to the inverse is swapped with the output of the restricted function. So this is something that happens with every set of inverse functions. The thing that makes these tricky, like we've mentioned quite a bit in the last section, is we have to be extremely careful with the domains and ranges. If you're thinking it back in terms of pre-calculus 1, the college algebra material, the exponential function and the logarithmic function did have domain and range issues as well, but it wasn't as finicky as this. So this is a little bit more in the complication. Essentially, anytime you compute any cosine inverse whatsoever, think in terms of this full table right here to always get on the right track. So on part E, we know function inverses with their functions should cancel, but the only reason this came out as exactly 5π/6 is because the input 5π/6 is in domain of the restricted function. Likewise, this one where we switched and put the function inverse inside, this one is just full undefined because 3 is outside the domain of the function inverse, arc cosine, or just written as cosine inverse for short on this table. It gets even weirder still. This one has no cancellation, and -π/4, that's restricted cosine, is not in the domain of that one whatsoever, yet this one is defined. What we did was we calculated cosine -π/4. It's √2/2. So we went to √2/2 on the x-axis. The one and only one angle that gets us to √2/2 in the range from 0 to pi is π/4. So this one comes out as an exact π/4. So these three together are pretty weird. They're good ones to practice, to wrap our minds around. And that gets us to the problem down here for the new one of the day. Cosine inverse of cosine 2.7163. Well, this one is not so bad because cosine 2.7163 is in domain. Pi is about 3.14 for rough approximation. So it did not exceed pi. That means this one has a full cancellation, and we just get 2.7163 to end the question on this problem. Well, those are the tricks and weird oddities with dealing with the cosine inverse. Same kind of issues with sine inverse. And now the table is now quite a bit different for tangent and tangent inverse. So that's going to be the next thing we take a look into. Any questions at all, folks? Finishing off that one down here. Okay, let's try it out all over again. So this was our warm up on what we did last time. Now we're on the last row here, and it's definitely different. The difference is for the restricted tangent function, we do have a restrictive domain we have to be mindful of. But for the range, anything goes. And it's even better for the inverse function, the range is all real numbers. And so that tells us it's a little bit less finicky with tangent and tangent inverse. But sometimes there's a little bit more guesswork here because tangent's the ratio of sine and cosine. So the values we have are often simplified, and we have to find the right values that give us the angles we're working with. So here's how it goes down below. We're focusing on just row 3 of this table. So paying keen attention to, not sure what happened. Hit Control Z again. I think the table is so close to the border that it just glitches out when I try to highlight. Let's try that again. So we're going to pay key attention to these domains and ranges, as well as these domains and ranges as we calculate. Okay, that didn't piss it off that time, so let's hope for the best. So it says, evaluate the following expressions, if possible, giving exact values. These are all tricky, so first thing I would do is, even if you're calculating tangent inverse, which is arctangent, you're still using a restricted domain. And that means you have a restricted range as well. These are the possible answers. So to organize that, a quick graph helps a lot. And this ties in how we did this in section 5.3 as well. On this graph, we have to be mindful with the fact that those are parentheses. It means negative pi over 2 and positive pi over 2 are not actual parts of this range, nor this domain. And here's how I would convey that information. On negative pi over 2 going this way, I'm putting an open circle there to say we can take all the values up to that point. So all of this stuff is fair game for the domain of the restricted tangent function. Then if we rotate in the clockwise direction, we can only go as far as positive pi over 2, that value there. So all these are potential answers for arctangent or tangent inverse, and nothing else. Everything else there is a restricted angle. So now next we're dealing with negative root 3 over 3. We're trying to come up with an angle, but sometimes it's good to just put down all of the angles that are on the table for this. First is radian measurement 0. Then it's pi over 6, pi over 4, and pi over 3. Notice all of these are impossible because that's a negative value. If you have a negative that you're working with, we had to have been in quadrant 4 down below here. So that eliminates a lot of guesswork. None of these are valuable to us. Tangent at any one of these angles is a positive value. So that's off the table, but then we go in the negative direction. The angles that could work for us going this way are negative pi over 6, negative pi over 4, and negative pi over 3. We can't actually use pi over 2 or negative pi over 2. Tangent at 0 is 0, so this one doesn't work as well. It's just down to these three. Tangent at negative pi over 4 is a negative one. So really, the guesswork comes down to either one of those two. Anyone spot which one would be the correct angle this time? I should put the red dot in a neutral spot while we're thinking about it. Kind of tricky in a way, right? It's easier with sine and cosine because you could just say, well, sine is at this angle is this value and work your way through it. But tangent is the ratio of those values. So if you're not sure, do this kind of elimination work and then just start calculating stuff. So I'm going to go and calculate this and just see what happens. If we get a negative root 3 over 3, we've found the angle. We don't, we move on to the next one. So it's basically trial and error. You can use even more targeted guesswork, but we'll talk about that once we find the answer. Let's start with this one. Tangent, negative pi over 3. Tangent is sine over cosine, and the sine value is at this height. It's negative root 3 over 2. Then tangent at negative pi over 3 is then divided by the cosine at that angle, which is here on the x-axis. That's at positive 1/2. This reduces to negative root 3. The divisions by 2 cancel off. And not quite. We have the root 3, but this one's divided by 3. That tells us we just move on to the next angle. Try out negative pi over 6. Tangent at negative pi over 6, thinking geometrically, will give us a sine in the numerator. That sine value is right here, exactly negative 1/2. Then come back up here. It's divided by the cosine value, which is here. That's the negative root 3 over 2, about 0.9 rounding. I said negative, that's a positive. It's clearly on the positive x-axis if we stare real hard. So it's positive root 3 over 2. This simplifies to negative 1 over root 3. And that's kind of concerning as well, right? We have negative root 3 over 3, but the difference is this has been rationalized to get to that value. So that's one of the reasons why it might be a good idea to practice rationalizing these things. One reason we rationalize them to this day is just to standardize our answers. So if everyone insists that they want a rational number in the denominator, we won't accidentally confuse ourselves to think negative pi over 6 isn't the answer, because it really is on this one. So multiply this by root 3 over root 3. We get negative root 3 over 3, and that means negative pi over 6 is the one that did it for us. So let's come back over here. The whole answer is negative pi over 6, because this check that we did works out. Tangent negative pi over 6 is in fact negative root 3 over 3. So it's kind of a tricky one. We did reduce the guesswork by picking the right angle, angles that would give us a root 3 over 3, angles that would give us a negative value for tangent. And the way you can really zero in on this is, if there's a root 3 in the numerator, it might have suggested this, because sine at a negative pi over 3 is a root 3 over 2. But the fact it's divided by 3 says that's impossible. This isn't divided by 3 at all. It had to have been negative pi over 6 on this one. But that's the kind of thing you would think about after doing lots of problems in the homework. And that's what the homework is going to be all about. Just a lot of this kind of practice. Again, it should feel kind of like deja vu, sections 5.2, 5.3. We're just doing things in a literal reverse way. Well, any questions, folks? Surviving that one? Okay, some of them go pretty fast. Recall not yesterday, but on Monday's class, we had that sine inverse of 0 equals 0, cosine inverse of 0 equals 1, and down below right here, or hang on, let me double check this. Cosine inverse of, I think I made that same mistake as before. Cosine inverse of 1 is 0. Let's fix that mistake in exactly the same kind of way. That's real deja vu now. But sine inverse of 0 equaling 0 is the same punchline over here. Tangent inverse of 0 is 0 as well, because in the check, tangent at 0, which would be sine of 0 divided by cosine 0, that just gives us value 0 over 1 equals 0. So that tells us some of them go pretty quickly. The zeros are kind of a nice giveaway. So are positive ones and negative ones. Positive ones and negative ones would correspond to angles pi over 4 or negative pi over 4. Anything involving a root 3 coming up, that's going to be either a pi over 3 or a pi over 6. So actually, there's not a lot of possible answers if we're just looking for exact values like we're seeing here. So part C is where it gets a little finicky. It's tangent to arctangent 27. And thinking in terms of what we did in just the very last portion of the notes, if we did something along the lines of cosine, arc cosine 27, this one's immediately undefined. That's because the input to the inverse function, arc cosine, exceeds 1 by a lot. It's nowhere in domain. It's far outside the domain. And even if this was a 1.000001, it's still undefined. The maximum value you can put inside cosine inverse is a 1. But tangent is special. The inverse arctangent has domain, all real numbers. So there is no way to build a trick question where the tangent inverse is on the inside. This is always, every single time, a full cancellation, and you just get a 27. If that was 27 times 10 to the power 30, you would get 27 times 10 to the power 30. Any number here will directly output a number there. All because the domain is fully the set of real numbers. So that's kind of nice in a way. Any questions at all, folks? Getting through that one?
What's the logic behind the full cancellation?
Oh, that's a great question. So one way to think about it is, let's maybe put down a graph for tangent to really see the full logic track. So I want to, there's a faster way to open that, but we got there. So the question from class is, what is the way to think about this logically? We're going to combine the logic with the geometry of the tangent inverse function, but we have to be careful because I have to plot this tangent function thinking of tangent inverse. So if we go tangent x, then I want an immediate restriction of negative pi over 2, less than x, less than positive pi over 2. In other words, we're just plotting tangent over one period. Now I want to set my scale to match the problem because we have 27 in this. But by the way, what is arctangent 27? Turns out that's about a 1.5. I guess where scale should do okay on this. So if you did arctangent of 27, you would get up to here, 1.5. So here is the number of 1.5377 and so on, right on that spot. So now that gives us some number over here. Looks like it's pretty close to 1, whatever that number happens to be. Oh, didn't mean to disappear that. So now if we take tangent, or hang on, I've got this slightly backwards. This is a good exercise, it turns out. I want that number to be, oh, I need the eraser. I want this number 1.5337 to be rather right here. So this is the number 1.53377, gives us a number out here, actually a little bit higher up, somewhere out here, giving us something in this range. So if we take tangent 1.53377, the more digits I put in, the closer and closer we're getting to 27. Let's see if that really tracks. 155, 1533, 7762, 1092. Looks like I'm getting pretty close, and I'd be even closer to 27 if I only had more digits. So arctangent took a value right here, reverses it, and gives us the 1.5337 here. Taking tangent 1.5337 just goes in the reverse direction and gives us a value in this location. So if we go tangent, arctangent 27, all we're doing is really reversing the arrows and getting the 27 back. But does that make sense in a way, seeing it that way through the calculator?
I think so.
Awesome. So arctangent 27, who knows what it's done to that number, but it gave us a 1.5377, some change. And then tangent just reverses that and gives us the 27 right back. So that's kind of the punchline to all the inverse functions. Whatever arctangent has done to the number, tangent reverses it, reverses the damage done to it, and gives just the number right back. Other questions at the moment? Okay, let's see if we can screenshot that table just for another look into the next ones. I think we can fit it right down below there. Oh, sorry, looks like I missed a chat as well. So that one would be undefined. Are you referring to the part D? Oh, part C would be defined. Tangent of arctangent 27 is defined and it equals 27 itself. And it's all because 27 in the arctangent function, which is tangent inverse, is inside the range. So this one would give you just the 27 and it would be defined. Does that make sense for that one so far? Oh, gotcha. Yeah, that's what's going to kind of happen a little bit with this one. The 7 pi over 4 is out of range, but part D is a lot different. This one is defined. These always feel a little bit weird. Yeah, absolutely. Thanks for asking about that. Other questions at the moment? Okay. Well, once again, some of these go in a really, really weird way. We took one where we're looking at 27 being in the domain, so we got a full cancellation of the function with its inverse. Now this one is totally different because the inverse is on the outside. The first thing we have to think about is, for the tangent function, we're thinking restricted tangent is 7 pi over 4 in domain, and it's absolutely not. 7 pi over 4 is coterminal to negative pi over 4, but they are absolutely not the same number. It's not in this domain itself. So this is the weird one where it's also defined, but we would work this one out using just ordinary order of operations. First, take tangent of 7 pi over 4. Let's do that on the right at that scratch work. Tangent 7 pi over 4. Well, 7 pi over 4 is in this quadrant, quadrant 4. So first you get the sine value, negative root 2 over 2. Then you divide by the cosine value. That's going to be positive root 2 over 2. And this whole thing then just cancels, becoming a negative 1. So we can start by saying this is just the same thing as tangent inverse of negative 1 itself. Then from there, well, if you have a positive 1 or negative 1, only ways that could ever happen is if you're dealing with a pi over 4 or a negative pi over 4. Well, it's got to be this one, it turns out, because tangent at negative pi over 4. Let's do a quick check on this part. Tangent at negative pi over 4. Well, in a certain sense, we did it once already, right? 7 pi over 4 is coterminal to negative pi over 4. So we would get the same exact conclusions. Sine value is still negative root 2 over 2. Cosine value is still positive root 2 over 2. So this is, let me try again, negative 1. So that would tell us that this angle right here is the output to the whole function. Tangent 7 pi over 4 is not a cancellation because you can just swap this to a negative 1. Negative 1 is in domain. The domain is the entire set of real numbers. So if we work inside out, we get a number. Now we can evaluate and get the negative pi over 4. Or just another equivalent way to think about this is the last time these came up, we thought of reflections. But this time, it was just a matter of placing 7 pi over 4 on this diagram and grabbing the right angle, negative pi over 4. So that would solve the whole problem on this one. I feel like this one, part D, is always really tricky, especially when we have domain issues that give undefined. Any questions at all getting through that part there?
Is the fact that the range is a set of all real numbers, is that just part of the definition of the tangent?
Yeah, absolutely. It's a consequence to this graph right here, y equals tangent x on negative pi over 2 less than x less than positive pi over 2 on that specific domain. That's the restriction here for the domain. This is a one-to-one function. So it's an invertible function. The inverse is y equals arctangent x. There it goes. That's a reflection across the line y equals x. But the fact that there's a vertical asymptote here and a vertical asymptote here at negative pi over 2, positive pi over 2 is the reason the range is all real numbers. It goes up without stopping. So every single positive number is swept out, and similarly in the other direction. So that's why we get that range there, just the consequence of how we restricted the function. And similarly for arctangent, the domain is the real numbers because when we reflect across y equals x, we've interchanged all the asymptotes, and now we have a full-on domain. But what's restricted now is the range goes from a minimum value, it'll never hit it, negative pi over 2, up to a maximum value, positive pi over 2, which is not a maximum inside this set. So we have to be mindful of that as well. Other questions at the moment?
I'm not sure I understand how you got through question D again. Could you recap?
Yeah, absolutely. So the idea of doing question part D was just calculate the tangent 7 pi over 4. So computing tangent 7 pi over 4 is what we did over here. And it's what gave us that negative 1 right there.
Oh,
And this is how we did the ones up above in the notes as well. But that makes sense on that correspondence there.
yeah, I see it now.
Awesome. And again, like I mentioned, these are really weird. So just to go back down memory lane as well, it was the same kind of situation when we were doing these, except part E, 5 pi over 6, was in domain of the restricted cosine, but the negative pi over 4 was the problem on this one. So part G is similar to the question that we just solved. Negative pi over 4 is in the restricted region. We can't get an output that's negative for cosine inverse whatsoever. So there was no cancellation on this, yet this one is also still defined. So what we did was just calculate cosine negative pi over 4, came out to negative root 2 over 2. So that's the value we see right, positive root 2 over 2. That's the value we see right here. And then from there, we could calculate arc cosine at positive root 2 over 2. It came out as the pi over 4 value. Again, these are pretty hard to see once we were seeing them from the very first time. These are really tricky problems. That's why it's really worth the effort to take our time with these. When you're doing them as homework questions, definitely always look at the table. This is like the Bible of what can be evaluated, what's undefined, what the answers are even going to be. The range is the full set of answers. And these drawings are extremely helpful as well. So, I mean, that's great in a way. We're just reviewing exactly how we computed in both sections 5.2 and 5.3. Other questions at the moment so far? Okay, looks like there's a couple more, but I don't think they're anything too crazy. The tricky ones were really parts C and part D, and they couldn't get excessively tricky like the sine inverse and cosine inverse, because the domain being all real numbers here does eliminate some of the trickiness. The things are most finicky when tangent inverse is on the outside. But just a last couple ones, just for the sake of a little bit extra practice. Here's the unit circle once again. We're going only from the range of negative pi over 2 up to positive pi over 2. That's the range of tangent inverse. So all of our answers lay on this band. When it comes to a root 3, this one's not so bad because root 3, not sure why I'm using that color. Root 3 would suggest either it's a pi over 6. Let me try again with that one. Pi over 3 is that angle, 60 degrees, or pi over 6 is this angle, 30 degrees. But based on how we did the part A on this problem, it ought to be this one, because we can check tangent pi over 3. I want to emphasize that this is just the check part of the problem. Tangent of pi over 3 will take a sine value, root 3 over 2 in the numerator, divide by the cosine value, which even on this shoddy unit circle, looks like it's roughly 1/2. We know it to be exactly 1/2 from experience. And it gives us the root 3. That tells us the answer to this one is pi over 3. So we're always going to have these two swapping each and every time we do this kind of work. So part E was, again, not as bad as these two up here. We did the tricky ones in the middle, like for no apparent reason. Last one is -1. Anyone happen to see what tangent inverse of -1 should be? Yeah, now I'm looking at my notes a little bit. That's kind of a redundant question in a way, right? It's looking right at us. So that was the harder problem. Here, if we didn't see that, pretend it's invisible for the moment. If we didn't see that up there, the way we'd probably think about it is whenever you take tangent of a pi over 4, you're always getting a +1 or a -1. So this pi over 4 is a candidate, except it's no good to us because tangent at positive pi over 4 is exactly 1. We're going for a -1, so we do the next best thing. At negative pi over 4, we'll get a -1. Again, it's the same thing as calculating tangent at 7 pi over 4, since they're coterminal values. So this one would be just a negative pi over 4. Kind of a silly last question because that was a little bit redundant in the notes. But this is the landscape of everything that can potentially happen on a homework question as well as an exam question, but this would be on exam 3 at this point. Well, these are pretty tricky problems. If you get kind of mixed up, don't hesitate to reach out by email, drop in office hours. I'll be happy to help out with these kind of problems. Keep the table near you. Keep drawing these kinds of sketches if it's been helpful, or maybe you have a really great mental chalkboard where you can just visualize these angles. That's great as well. And it helps a lot getting through these kind of problems. The thing that helps the most is just practicing a bunch of problems. So for the actual homework exercise in section 6.3, it looks like a lot once it loads. Canvas was supposed to be fast, but here we go. That's not the homework. Maybe that's why it wasn't taking a while. Here's the actual homework. Looks like a lot of problems, but they're pretty fast drill sort of questions. So work through these. They're similar to the ones we've solved. It'll give you a great feel for how these kind of computations go. We did it, folks. That's the entirety of section 6.3. This is due after the day of exam 2. So if you focused on these sections, until after Monday's over or after your scheduled exam is completed, that would make sense. Even if this goes, you turn this in past October 15th, I will still accept it for full credit. So think of all the due dates in this class as really just pacing. Once it goes past this date, I do put in a grade. So if you missed it, you might get a grade of 0. But if you turn in your homework a little bit late, I will grade it for full credit. So we're turning to next, section 7.1. Usually it's a good idea to save these and close them. Give us a bit of a mental break. We're kind of pushing Microsoft Word to its brink with this computer. This is not the fastest computer they gave us this semester. So one document at a time is probably a good idea for Microsoft Word. So now we're going to take a look into trigonometric identities and equation solving. Sections 7.1, 7.2, 7.3 are all going to be about trigonometric identities. So it's going to be a collection of all the trigonometric identities we've seen so far and some new ones along the way. Here we're taking a huge different approach from the trigonometry we've seen so far. The trigonometry we've been doing could be thought of as kind of a geometric trigonometry. I mean, we've been drawing geometric objects a lot, but now we're going to be doing this kind of stuff. We're looking at just formulas and the such. This becomes more of analytic geometry, or excuse me, analytic. Trigonometry. What we mean by analytic trigonometry is we're trying to say everything we can say, all there is to know about the trigonometric functions through identities and various other formulas and properties of the functions themselves. So there's not as much graphs at all in this chapter. We'll cite a graph anytime it makes the most sense. But for the most part, we're just looking into these identities. This is the rundown of the identities we've had so far. But what makes this tricky is we need to say once and for all, what do you even mean by an identity? If we don't say what that is and get a good mental feel for it, it makes this entire section, this entire chapter, all just one foggy mess of lots of symbols that we're pushing around. So that's the purpose of the warm-up example here. In the land of equation solving, which is the ultimate goal of chapter 7, solving trigonometric equations, there's really 3 kinds of equations that we deal with. There's conditional equations, contradictions, and identities. This seems to be a big part of what this chapter is about, so that's the correspondence here to here. First, when most people think of an equation, this is about what you're thinking about, something that's a conditional equation. I didn't try to put down a fancy equation that needs quadratic formula or something crazy, just really we're focusing on the concept. So solving this equation would give us the solution, x is 4. But really, this is a sentence. The sentence here goes like this. It flows by saying, if 2x equals 8 is true, then we have an implication, x is equal to 4. So this is just a whole sentence that we often don't write in the actual words in or put a period, but that's what we mean by a conditional equation. It's an equation that's true on the condition that you selected the one and only solution, x itself takes the value of 4. So that's what makes it conditional. Its truth is conditional on x being 4. If x is 5, it turns out to be a false statement. It's just a total lie. So those are the equations we know, we've loved, we've practiced all our lives, it might feel like, from middle school, high school, and so on, possibly in elementary school as well, hopefully. Then the contradiction is where algebra gets a little bit weird, but it kind of makes sense when you say contradiction. Contradiction should be something that is illogical, something that's totally false, something you can never make true, you can't repair this. And this one is a contradiction because the moment you subtract 2x from both sides, which is the only step you can take in solving this, subtract 2x, you get the statement that x equals 4, which is false. So it doesn't matter how weird the math class gets, this is a false statement. But what makes this a bona fide contradiction is that the falsity of this resulting statement that flowed from the original equation had nothing to do with x. Pick any x you want, and you have a false statement out. So we have a contradiction because the falsity, let's say it this way, contradiction, because the falsity, I'm not sure if that's a real word, but let's go with it. The falsity or the falseness of that statement does not depend on a value for x. X is irrelevant. So that's what contradictions look like. They're the total opposite of the identities. And we like trigonometric identities because they can take something complicated. Here's something complicated. And we can make it simple. If we use the right identities, we can take this weird expression here and turn it into something nice. Well, that's the whole punchline to this section. That's something you actually do quite a lot if you're taking Calculus 1, Calculus 2, Calculus 3. You'll occasionally run into trigonometric expressions just like that one, and we have to clean it up before we do any work with it because it's just a mess as it stands. Identities are the machinery that help us get there, so we should say what we mean by an identity in the first place. First, let's just do some basic algebra. We can divide 2 into the left-hand side. We're effectively using the distributive law with the 1/2. We get x plus 8 equals x plus 8. And here you could subtract off the x if you like, but let's just leave it right the way it stands right here. Oh, by the way, I noticed a mistake I made in my contradiction equation. If I subtract 2x's from here and from here, I should have gotten a -4, right? Let's actually fix that. Still false, but the logic was not quite sound to get to that false statement. That's the fix with the negative sign. But this one, it's identical on the left-hand side. It's identical on the right-hand side. I won't even mess with it from this step on. This is true. And it is true for all values of x. That whole statement there, the fact that any value of x you can pick, any value of x that's valid in a domain, if we have a domain restriction, gives us a true statement. So this makes it an identity. So the paraphrase here is contradictions are statements that are always false. Identities are statements that are always true. And conditional equations, we'll look into those at the end part of chapter 7, are things that depend on x. It's either true or false. So on the next page is our roundup of identities. These are things that we've seen already in chapters 5. This is information we got in chapter 6. We were using the fact that functions are periodic. And this is just another way to convey that. Sin x repeats on any multiple of 2 pi. So does cosecant. So does secant and cosine. Tangent and cotangent are the odd ones out because they repeat on a period of pi itself. So pick any integer k, it could be 10, -3, 4. And if you use periodicity, sin x, add or subtract any multiple of 2 pi, gives you just sin x back. We have the even odd identities. We'll look into these a little bit more that we explored briefly in chapter 5. And this was just the definition of the trigonometric functions. So that's the whole set of identities we have on the table so far. We'll just be practicing with them, actually working with them in a stronger way as we work through this section 7.1. Our major objective is to clean up this stuff, try to write things in as simple of a way as possible. Well, any questions at all, folks, before we call it a night? Okay, seems like a good stopping point. We're not going to try to rush through a problem in less than a minute. We'll return to these notes when we come back on after the exam. That's going to be the 15th. So the due date might be the 22nd, but I think rushing through these notes in one day essentially is going to be tough. More likely the due date is going to be the 27th on this section 7.1 assignment. So we'll take a breather on the course, get through exam 2, and then come back here a week away from today. Have a great night, folks. I'll see you all after the exam. Oh, thanks for mentioning that. Thanks, folks. It's just going to be sections for the midterm, which is also exam 2. It's just going to be 5.4, 6.1, and 6.2. And check out the sample exam problems as well for great practice on those. Well, take care, folks. If you have any questions while you're studying over the weekend, don't hesitate to reach out. I'll be happy to help. And I try to check my email more often when we're going across into an exam week, since I know there's probably definite questions coming out. But if I don't see or hear from you till Wednesday, have a great weekend, y'all. I don't know why I said y'all. I'm not Southern. Yeah, absolutely. If there's a conflict with the testing center, that'd be just fine.